In this video, we'll introduce some fundamental concepts associated with Fourier transform or frequency domain analysis. And we'll introduce a couple of different applications where frequency domain analysis is extremely useful. Most of you are familiar with the idea, hopefully, of frequency. It's the rate at which a signal or some physical thing wiggles, basically. Manifestations of frequency in the physical world, if you think about sound, the pitch of the sound is determined by its frequency. If you think about electromagnetic radiation, then frequency determines what kind of radiation it is. So, for example, if you're looking at electromagnetic radiation in the visible frequency bands, then the frequency determines the color of the light. Frequencies higher than visible light lead to ultraviolet light, and then up to X-rays and even gamma rays. So frequency also determines the energy associated with photons. So there's, again, a lot of different ways in which frequency shows up in the natural world. There's also ways that it shows up in physics that aren't so much due to the natural world, but we use frequency domain analysis to solve things. This graphic is a picture of a simulation or a computed temperature of a heat sink, where over on this edge you've got some hot CPU or something else, and out here you have cooler temperatures. This heat, the distribution of heat within the heat sink obeys the heat equation, and the heat equation was solved using frequency domain analysis. Not that there's an intrinsic frequency associated with heat, but that the techniques, the mathematical techniques of frequency domain analysis make solving these sorts of problems possible. Now, in all honesty, the heat distribution you see here, from hotter to colder, was computed using finite domain or finite mesh analysis on a computer. But Fourier domain analysis also allowed these sorts of things to be computed before computers could do this. Fourier analysis has also been used to compute vibrating strings or solve frequencies and nodes and such in vibrating strings. And orbit determination is actually mathematically a very powerful tool and allows you to find solutions to partial differential equations that otherwise couldn't be found. In engineering, we use the concept of frequency in a lot of different ways. One way in which we use frequency is when we think about a communication system. So what I have here is a cell phone, and this cell phone communicates with radio waves to a base station or a tower. And I have actually several cell phones, so I want many cell phones to communicate to the base station. And it turns out that one of the issues you face is that if both cell phones are using the same frequency, then unless you do things in a very clever way, these frequencies collide with each other in some sense, and you don't get good information at the base station. Now, it turns out that, well, in just a minute I'll give you the proviso here. On the other hand, if each cell phone transmits in a different frequency, then at the base station I can sort out which transmissions are coming from which cell phone by looking at the frequencies that they transmit. And that's actually the way that AM radio, FM radio, cable TV, analog cable TV at least, and many other communication systems work. Now, again, in the spirit of free and clear disclosure, it turns out that in many cell phone systems, you will have two cell phones transmitting on the same frequency, and they use other techniques such as time division multiplexing or code division multiplexing to separate the information from the two cell phones. So this idea, though, that I can use different frequencies to transmit different stuff has been used since basically we started with radio a century ago. So this principle applies to cable television, to digital and analog communications, and in fact frequency bands are allocated for each of these different purposes in almost every country. Okay, so that is, and looking at things in the frequency domain allows you to design these systems. So most communication systems are designed by doing frequency domain analysis. Another reason to do frequency domain analysis is given by this cryptic set of pictures, and let me try to explain here. The idea is that if I have a signal, so in this case, this is an awful looking signal, but we'll pretend like this is a signal. So I have a signal, and this is drawn as a function of time. It turns out that any signal I can represent like this as a function basically of time, I can represent it also in terms of sines and cosines at particular frequencies. And that's what this picture here is showing. So I have this square wave, and in the top picture it's showing that I can sort of approximate this square wave with a sine wave. And you can see that the sine wave goes up where the square wave goes up and down where the square wave goes down. But it's not a square wave. It turns out by adding another sine wave to my first sine wave, and this second sine wave in this particular case has a frequency 3 times the frequency of this sine wave here. By adding that, I get something that looks like this, which is closer to my square wave. By adding yet another sine wave that has a frequency of 5 times the fundamental frequency of this guy, you can see that I get even closer. By adding another sine wave with a frequency 7 times my fundamental frequency, I'm getting even closer to the square wave. And the idea is that I can take the square wave and break it down into a sum of sine waves. This turns out to be an extremely useful thing to be able to do. For example, it turns out that this is quite similar to the process that your ear uses to process noise and sound, and from that noise and sound make meaning of the world, or make sense of the world. It turns out that these higher order harmonics, so the third, or the sine wave with 3 times the fundamental frequency, 5 times the fundamental frequency, and 7 times the fundamental frequency, these are called harmonics, and higher order harmonics basically change the sound of a musical instrument, for example. So a flute typically does not have a strong harmonic component. Brass instruments typically have much more harmonic or much stronger harmonic components. But harmonics basically determine what the music sounds like. Or things like speech recognition and speech compression use the idea that I can break signals into different frequencies. And so, for example, in speech compression, you might take a signal in the time domain and convert it into a frequency domain representation, which might look something like this. So this is frequency. This is actually power at every frequency in the signal. And then you might compress this signal by representing its frequency domain characteristics by a bunch of straight lines, except if you draw like I do. And these straight lines you can transmit over a communication channel with much fewer bits than you can the whole frequency spectrum. This brings us to another idea. All of this sorts of, the compression to give you MP3 or to do speech recognition and stuff like that, all of this is done on a computer. And it turns out that Fourier analysis allows us to look at signals. Say, for example, I've got some arbitrary signal that looks like this. This might be speech or the stock market or something that you're interested in. And by using Fourier analysis, I can determine how many samples I need to take of this signal. So a sample basically is just looking at the signal at a particular point in time. So you can basically see how many samples of this signal I need to take in order to be able to reconstruct the signal with a given degree of accuracy. And this turns out to be extremely important because in order to process a signal in a computer, you need to have the signal be sampled. Computers don't operate on continuous time signals. They operate on sampled signals. And so by using Fourier analysis, you can determine how far apart your samples need to be spaced. And again, then you can take these samples and turn them into, zeros and ones, different patterns of zeros and ones which go into the computer. And you then do whatever you want to do in the computer. Turn it into stuff that you're going to post on YouTube or whatever it is you're going to do. So this is an introduction to the frequency domain and analysis and the sorts of applications that you'll see this used in.